Hi students, now in this video lecture we will go through second colligative property, which is elevation and boiling point. So boiling point, we know boiling point is the temperature at which vapor pressure of any liquid is equal to the atmospheric pressure, right? When vapor pressure is equal to the atmospheric pressure, at that temperature the liquid will start boiling. For example, the most common example we know is of water. We know that boiling point of water is 100 degrees Celsius. That means atmospheric pressure equals to the vapor pressure, right, of water at 100 degrees Celsius, right? So now elevation and boiling point, and we say elevation and boiling point is a colligative property. By saying colligative property, it means elevation and boiling point depends on the number of solute particles, right? So something is happening to the normal boiling point when some solute is added to a solvent, right, or any liquid. And elevation and boiling point is by adding this solute, right, the boiling point is increased. The temperature at which a liquid normally boils, that temperature is increased when a solute is added to it. Since it's a colligative property, so we are adding some kind of solute to it, right? So this increase in temperature, right, when a solute is added to a solvent is known as elevation in boiling point. Now let's understand it. Okay, one thing to understand this, you should know, you should be aware of concept that we have done before of lowering in vapor pressure, right? Relative lowering in vapor pressure and Raoult's law. So this is the graph, and first let's understand it. So normally when we take pure water or any pure liquid, for example, this is a pure liquid, right? This is a liquid and we have molecules of liquid on it, right? And at the surface we know that vapors that are formed due to the molecules of liquid that are at the surface of the liquid, right? And the molecules that acquire enough kinetic energy to overcome the intermolecular force of attraction between the liquid molecules, because these liquid molecules are being attracted by the other molecules also as well, which is known as intermolecular force of attraction between molecules. So the molecules which acquire enough kinetic energy to overcome this intermolecular force of attraction will escape into the gaseous form or will escape into the vapor form, right? And all these molecules that can escape into the vapor form will build vapors right above it, and due to these vapors will exert pressure, right? So the pressure due to these vapors is known as vapor pressure. So this is the case when no solute is added to it. Now let's take an example. Now let's add salt to this water. And at this, let's take common example of water, and in this condition water boils at 100 degrees Celsius, right? Say at this temperature, in this case water boils at 100 degrees Celsius when no solute is added to it. Now let's add salt to it. When you add salt to it, we know that some of the liquid molecules at the surface would be replaced by salt particles, right? So for example, before there were 10 molecules, so when you add solute to it, some of the solvent molecules would be replaced by solute particles or solute molecules, right? So when solute is added to it, these liquid molecules are replaced by these green solute particles, and thereby the number of solvent molecules are decreased at the surface. So when the number of solvent molecules are decreased, less solvent molecules would move into the vapor phase. So when less molecules will move into the vapor phase, we have less number of vapors above the liquid. Less number of vapor means less vapor pressure, right? Now since we know that water boils at 100 degrees Celsius when the vapor pressure becomes equal to the atmospheric pressure, right? When we know that vapor pressure should become equal to atmospheric pressure, right? So in the case of pure water, this vapor pressure of this water becomes equal to the atmospheric pressure, right, say at 100 degrees Celsius, right, because there were no solute particles, so all liquid molecules could escape into the vapor phase to build the vapor pressure, right? But now when solute is added, we have less liquid molecules, so less vapors would be available. Say let's say now we have less vapors, right? So now how can we increase the vapor pressure of this solution, right, so that it can become equal to the atmospheric pressure? Atmospheric pressure we normally take as 1. The only way liquid molecules can escape into the vapor phase is when we have enough molecules, liquid molecules on the surface that have enough kinetic energy to escape into the vapor phase. Now what we will do is we increase the temperature. Since we have less molecules, so now we will increase the temperature of this liquid. Now when we increase the temperature of this liquid, more liquid molecules will acquire enough kinetic energy. We know that when we increase temperature, kinetic energy of liquid molecules will increase, because kinetic energy we know is directly proportional to temperature. So when we increase temperature, kinetic energy of molecules will increase, so they will move to the surface, right, and will move into the vapor phase when we increase temperature. So in order to make the vapor pressure of this solution, since now it's a solution, when you added solute to it, we have to heat it to a slightly higher temperature so that more molecules could acquire enough kinetic energy to escape into the gaseous phase or vapor phase. So we have to heat it, let's say we now heat it to 105 degrees Celsius to build the same vapor pressure as it was there in the pure water case, right? So what this addition of solute has resulted? This addition of solute has resulted into increase of temperature, right? So as to make the vapor pressure equal to the atmospheric pressure. So this is known as elevation and boiling point, right? And this elevation and boiling point depends on the solute added, because when we added solute to it, the added solute has caused the vapor pressure to fall down. Then we increase the temperature to increase the vapor pressure so as to make it equal to the atmospheric pressure, right? So that the solution will again start boiling, right? So the elevation and boiling point, we say, depends on the concentration of solute, right? And when we talk about, in connection to boiling, elevation and boiling point, when we talk about concentration of solute, we'll be discussing concentration in terms of molality. Molality is number of moles of solute dissolved per 1000 grams of solvent, or per kg of solvent. Number of moles of solute per kg of solvent or per 1000 grams of solvent. So this is what we have already learnt, that since vapor pressure increases with temperature, so solution has to be heated, right, to a high temperature to make its vapor pressure equal to atmospheric pressure. So this resulted in elevation of boiling point compared to pure liquid. Now the same can be seen from here, right? This is the graph that explains exactly what we have learnt here. These are two graphs, right? The graphs below is for solution and above is for solvent. Now graph for solution would always be below that of solvent, because the vapor pressure of solution we know is always less than that of solvent because of added solute, right? So if you look at this graph, this is atmospheric pressure, that is when the vapor pressure of this solvent and solute becomes equal to the atmospheric pressure, this solvent or solute will start boiling. Now let's see at what temperature the atmospheric pressure of solute and solution will become equal to the atmospheric pressure. For solvent, we can see that the atmospheric pressure would become equal, the vapor pressure would become equal to the atmospheric pressure at temperature TB0, TB naught or 0. So, right, and for solution, we know that in case of solution, as we have gone through above, there would be increase in temperature, right? Like we here increase the temperature. So for solution, we will see that the vapor pressure would become equal to the atmospheric pressure at a higher temperature, which is TB, right? This is TB is higher than TB0, right? TB is greater than TB0. Why? Due to added solute, right? So this difference between TB and TB0 is elevation in boiling point. This is the increased temperature, right? This is the temperature that we increased so as to make the vapor pressure of solution equal to the atmospheric pressure after addition of solute. So this is elevation in boiling. This delta TB represents elevation in boiling point, right? So now we'll just go through the expression for elevation in boiling point. We would be using this expression in our numericals, right? So here the expression, we know that, like I've explained before, that the elevation in boiling point depends on the concentration of solute, and when we talk about concentration of solute in connection to elevation of boiling point, we mean molality, and molality is number of moles per 1000 kg, per kg of solvent. So depends on the concentration of solute in solvent and has been found to be related with molality. This expression for elevation in boiling point is a relation between concentration of solute and elevation in boiling point, right? This expression just shows you the relation between, I'll repeat, elevation in boiling point, right, and the concentration of solute, because elevation in boiling point resulted due to the added solute. So the relation between them is delta TB is equals to Kb M. M stands for molality, right? And Kb is your molar elevation constant, which we also call it as ebullioscopic constant. So this constant Kb, if we take one molar solution, by one molar solution we mean 1 mole. By 1 molar solution we mean that 1 mole of solute is added to 1000 grams of solvent, right? So when M is 1, that is when the molality of solution is unity, when the molality of solution is 1, the molar elevation constant is equal to the elevation in boiling point. I repeat, when molality of solution is 1, is unity, then the molar elevation constant or ebullioscopic constant is equal to the elevation in boiling point, right? Now, since in the beginning we said that it's a colligative property, right? Elevation in boiling point is a colligative property, so let's prove it. Since we know that here this delta TB, elevation in boiling point, is directly proportional to lowering in vapor pressure, right? How? When the vapors are less, suppose when we added solute here, the vapors become less, right? And the more is this less vapors, we call it as lowering in vapor pressure. So the more the vapor pressure will go down, right? More the vapor pressure will go down, the more you have to heat this solution so as to make its vapor pressure equal to the atmospheric pressure, right? So we say delta TB is directly proportional to lowering in vapor pressure, right? And we know that lowering in vapor pressure from Raoult's law is directly proportional to the number of moles of solute, right? Which is clear from here. More the number of solute, right? More we add the solute, more will be the lowering in vapor pressure, because more is solute means more number of liquid molecules would be replaced by the solute molecules. So less liquid molecules will escape into vapor phase. So we say that lowering in vapor pressure is directly proportional to the moles of solute, right? So N2 is the number of moles of solute, hence so we say that delta TB, since delta TB is directly proportional to lowering in vapor pressure, and lowering in vapor pressure is directly proportional to number of moles of solute. So this elevation in boiling point is also directly proportional to number of moles of solute. And we know that if the properties that are directly related to the number of solute particles are colligative property, so from here we proved that this delta TB, which is elevation in boiling point, is directly proportional to the moles of solute. Moles of solute is the number of solute particles. So this proves that elevation in boiling point is a colligative property, right? This is important. Now let's derive this expression. How can we derive this expression of which is a relationship between elevation in boiling point and the solute added, right? And the elevation, this is a relation between elevation in boiling point and the concentration of solute. Molality is nothing but concentration of solute. From here we know that elevation in boiling point is directly proportional to the lowering in vapor pressure, right? So we use this from Raoult's law. This elevation in boiling point is directly proportional to the lowering in vapor pressure, right? And as per Raoult's law, we know that lowering in vapor pressure is directly proportional to the mole fraction of solute. Mole fraction is the ratio of the number of moles of solute to the total number of moles in solution. So if we calculate the mole fraction of solute, it's number of moles of solute divided by total number of moles in solute. This N1 is number of moles of solvent, N2 is number of moles of solute. So this is total number of moles of solute, total number of moles in solution, and this is number of moles of solute. So X2 would be mole fraction of solute would be N2 upon N1 plus N2. And we know that N1 is the moles of solvent, which is very much greater than the number of moles of solute, right? So N2 can be ignored in the denominator, right? So we can write it as this expression as X2 is equals to N2 upon N1, right? So X2, and we know that number of moles is mass upon molecular mass. So W1 is the mass and M1 is the molecular mass of solvent, right? So we'll replace N1 with W1 upon M1. So this is the expression for mole fraction, right? And now since delta TB we said is directly proportional to the mole fraction, right, of solute, so we'll replace this proportionality with a constant and we'll place this value of mole fraction in this expression, right? So it will become K, right, M1 N2 upon W1, right? And N2 upon W1 is your molality. What is molality? I repeat, molality is number of moles of solute, which is N2. N2 is the number of moles of solute per 1000 kg of solvent. This W1 is mass of solvent. So if W1 is equals to 1 kg, then N2 upon W1 is nothing but molality, right? So if W1 is 1 kg, then its N2 is number of moles of solute per kg of solvent.